Welcome back. Well, if I remember right, I left off at the bottom of the previous page. Correct me if I'm wrong. First thing we have here is conservation of momentum can be thought of as following from Newton's third law. And also the second gets thrown in there before we're done. I'm not going to derive that in general. I'm going to more like illustrate it with a special case. And, that kind of gets the idea across anyhow. And that special case would be, I guess that's good enough right there. Focus, thank you. People who cleaned up in here last night broke my piece of chalk. How inconsiderate. Anyhow, I've actually got more, but let's consider a collision. Momentum methods get applied to collisions quite a bit. Example. This could be two balls on a pool table, for example. Ball number one and ball number two. Or they could be two cars colliding on a highway. It's just they look a lot more like balls on a pool table the way I've drawn them. This picture is supposed to be at some point while the collision is in progress. Okay, I mean, collisions don't last very long, just a fraction of a second typically, but this is at some point during that little fraction of a second when these two billiard balls are pressed against each other during the collision. So ball number one exerts a force on ball number two, which I'll call F1 on 2, seemed like a good name. And because of the third law, ball 2 is pushing back on ball 1 at the same time. Force that 2 exerts on 1. So if this ball was just sitting there, for example, and this one comes along and runs into it, this force will make this ball pick up speed during the collision, and this force will make this ball slow down. Because of the third law, these forces are equal and opposite. So the force that 2 exerts on 1 equals the negative of the force that 1 exerts on 2, equal and opposite. Multiply both sides by the time. Should listen to myself. Almost left out the delta t. If you want to oversimplify what's going on during the collision and think of a constant force, then delta t would be the duration of the collision, how much time the collision lasts. More realistically, the force will change as the collision progresses. What you would have to do is take the total amount of time that the collision lasts divided up into a lot of much smaller time intervals and integrate. But in that case, delta t would be, well, you know, like I said, I wasn't going to be completely general. I just wanted to illustrate the basic idea. So if you want to oversimplify and think of a force that suddenly appears, remains constant, and then disappears again when the collision ends, then delta t would be the amount of time that the force lasts. And if you want to get more realistic, a more elaborate version of this same argument will hold true. So F delta t, this is the impulse acting on ball number 1, and over here we have the impulse acting on ball number 2. And from what I said in the previous recording, the impulse acting on an object is equal to the change in its momentum. So the change in momentum of ball number 1 equals minus the change in momentum of ball number 2. Well, with delta anything, whether you're talking about change in momentum or change in temperature or whatever it is you're talking about, increases are positive, decreases are negative. So this says, well, maybe it's better to think of the balls going that way than what I said earlier, but this says that the momentum gained by ball number 1 is equal to the momentum lost by ball number 2, which is to say that the total momentum between the two of them stayed constant. So writing that out in a little more detail, I guess if ball number 1 was going that way, it would be losing momentum, which would actually make this delta P negative and this delta P positive, and they're still negatives of each other, so it doesn't matter. So to repeat, equal and opposite forces means equal and opposite impulses. Equal and opposite impulses means equal and opposite changes in momentum, which means that if you add the momentum of the two of them together, the total stays constant, which I will write down over there in just a couple of seconds. I've illustrated this for one particular type of force, but it would be true in any situation because the third law is true in any situation. Instead of two balls running into each other on a pool table, it could be two asteroids interacting gravitationally as they pass near each other. And actually, it doesn't have to be two objects. A more elaborate version of the same argument would apply if it was a whole cluster of 17 asteroids interacting with each other gravitationally. It would take a lot longer to account for everything, but in the end, because the momentum changes are equal and opposite, for any pair that you pick out of this whole group of objects, in the end, the total momentum is going to stay constant. So here comes the part with the box around it. So far, that says when external forces can be neglected, Neglected meaning, you know, they're so small compared to the collision forces that they don't make any difference to the level of accuracy we care about. To phrase that another way, we have an isolated, focus, thank you, isolated system. External forces, well, first of all, by a system, I just mean some kind of a collection of objects. 2 balls on a pool table or a bunch of asteroids or whatever you're talking about. You have some kind of a collection of objects that is under consideration. If there are any forces acting on some part of this system from outside, that force from the outside could put more momentum into the system or take some away, okay? But to the extent that external forces are small enough to ignore, then for the reasons I just described, total momentum is constant. That is an idea as fundamental as conservation of energy, which I talked about last week. Conservation of momentum. Momentum methods, well, it's true in general, but as I've said before, you have alternatives. There are different approaches that you could take to a problem, and momentum methods seem to be particularly well suited to collisions because external forces are always just dwarfed by the forces of the collision itself. If you go back a page or two in your notes, for example, problem number 3, section 6, problem 3, was that collision between the car and the insect, okay? Now the insect had a mass of 1 gram, which, as an example of an external force, the weight of a 1 gram insect is in the neighborhood of 1/100th of a Newton, compared to the force from the collision, which was around 20 Newtons. That's 2,000 times greater, okay? And this is typical. Forces from collisions tend to be large compared to whatever other forces might be acting on the objects involved. For the brief time that the collision lasts, things like friction and gravity and so on have very little effect compared to the big forces from the collision. So to an excellent approximation, colliding objects can be thought of as an isolated system. So conservation of momentum is often a good way to approach them. I don't know as necessarily all the problems in the homework for this section are collisions. I'd have to go back and look, because like I said, this can be applied to other situations also, but certainly a lot of the problems are collisions. Well, actually, the first example I'm going to do is not technically a collision, but it's kind of like a collision taking place backwards. Instead of 2 things running into each other, it's something popping apart. If you took a video of it and played it backwards, it would look a lot like a collision. So if it ever comes into focus, that says, the camera over there? Ah, that did it. You're firing a gun, and it gives the mass of the gun, the mass of the bullet, and the muzzle velocity of the bullet. And you're supposed to calculate the speed of recoil. We're up here if you're trying to find what I'm talking about. Since momentum is conserved, if you consider two different times, which I'm going to call before and after, the total momentum at those two times has to be the same, because that's kind of what conservation of momentum means, okay? I like to draw little pictures, as with other types of problems. So here we have a not particularly well-drawn gun, but it's got a mass of 4 kilograms, 4.00. Just after the collision, we'll say it's moving in that direction before your shoulder has a chance to slow it down any. There's the bullet, a few inches in front of the gun, going 500 meters per second. It's got a mass of 8 grams. So that's the situation afterward. If I was going to draw a before picture, it would just show the gun with the bullet inside of it, both of them sitting still. Drawing another picture sounds like more work than it's worth in this case. So I'm just going to kind of put in parentheses that before you fired the gun, everything was at rest, okay? So conservation of momentum means the total momentum in your before picture equals the total momentum in your after picture. P initial equals P final. And we don't need a full-blown vector treatment because it's a one-dimensional problem. Everything stays on the x-axis, so we can handle the directions just with plus and minus signs. Because everything is at rest, P initial equals 0. And as for final momentum, that would be mv for this object plus mv for that object. Converted grams to kil. Actually, you could get it to work if both masses were in grams. What really matters is just that you use the same unit everywhere. But what we were given is 1 in kilograms, 1 in grams. One way or another, you have to make them match. So converted grams to kilograms to match that one. A couple lines of straightforward algebra, and we'll have the answer. 500 times 0.008 is 4. Subtract the 4 from both sides. Divide both sides by 4. The reason the answer comes out negative is it's a matter of the direction. I assumed the bullet was going in the positive direction. Since the gun's going the other way, it gets a negative velocity. It's headed toward the left. Actually, I shouldn't probably have said that the gun hasn't touched your shoulder yet. Firing a gun that way is a good way to get a bruise on your shoulder, but if you did, this would be the velocity of the gun. Next problem. Before we get to the next problem, an incidental comment. The same effect that was just illustrated in this problem I did with the gun and the bullet, that's how a rocket works, basically. If you go back into the history of the subject, in the very early 20th century, there were people who argued that rockets shouldn't be able to work in space because there's nothing to push against, which just goes to show there's always somebody around who doesn't know what the heck they're talking about. If you're interested, Google it and read up on that a little more. The way a rocket actually works is, well, you could call it action and reaction. You could call it conservation of momentum. As I was saying earlier, they're kind of the same thing. But instead of expelling one big bullet all at once, like a gun does, the rocket is constantly expelling a large number of little microscopic bullets, which would be the molecules of burning fuel, which are being expelled at a very high speed out of the back of the rocket. As the rocket continuously throws fuel in one direction, the rocket experiences a continuous recoil in the other direction. And that's how it develops thrust. Unlike airplanes, for example, or any kind of a aircraft that's designed to operate in the atmosphere, airplanes kind of sort of swim in the atmosphere. And if there isn't any air, they don't work. In fact, you can go higher in a balloon than you can in an airplane. But a rocket, as you know, works just fine in a complete vacuum. And that's how it does it. It's, you give the fuel momentum in one direction, and the rocket has to acquire some momentum in the other direction. Or in terms of Newton's third law, if there's a force on the fuel throwing it in one direction, there will be a reaction force on the rocket throwing it in the other direction. So that's the story of rockets, kind of abbreviated. Number 6 is a collision. Could be two balls on a pool table, except the numbers aren't quite right. Balls on the pool table would have the same mass, and I made them different. And this is a little on the heavy side for billiard balls also. But aside from that, it's something kind of like that going on here anyway. So here they are approaching each other. We're going to say the origin is the point where they collide. And here we see them shortly after the collision, moving away from the collision site in the direction, well, I give you the magnitude and direction for what this ball is doing. The speed and direction of the other one are unknown. And it's our job to figure that out. A brief pause to create some suspense in the audience. And here's how we do it. As with the previous question, it's conservation of momentum, only this time it's a two-dimensional problem, so we need a full vector treatment with, you know, I's and J's and that sort of thing. I don't need to draw my before and after pictures because there were before and after pictures in the question. So referring to those pictures, the 3 kilogram object was going right straight down the x-axis at 7 meters per second. Momentum, mass times velocity. So there's its mass, there's its velocity vector. The 2 kilogram object was going right straight up the y-axis at 4.5 meters per second. So that's the total momentum of these two things before they hit each other. That has to equal the total moment, and of course momentum is a vector. The direction as well as the magnitude has to be conserved. The center of mass of these two objects moves along a straight line at a constant speed. The individual objects get deflected, but P final has to equal P initial. So after the collision, the 3 kilogram object times, well, do the usual thing to get the components. It's going 3.5 meters per second. Direction is 60 degrees above the x-axis. So hypotenuse times cosine gives you the x component that I wrote there, and hypotenuse times sine gives you the y component that I wrote there. So mass times the velocity vector, that's, oops, wait a minute, wrote that in the wrong place. That doesn't belong outside the parenthesis, that's just multiplied by the y component. There, that looks a little better. The 2 kilogram object, its velocity is the unknown I'm looking for. So I'll just call its velocity v. And the idea is to solve for that. Well, usually the setup is the hard part, and we've got that behind us now. What's left is just crunching through the math. 7 times 3 is 21. That times that is 9. That times the cosine is about 5.25. I think it's probably exactly 5.25. That times the sine is 9.09. I'm going to carry one more decimal place because it comes out so close to that. Combine the like terms, the I term with the other I term, the J term with the other J term. So I subtract the 5 1/4 I from both sides. Subtract this from both sides, and then combine it with this other term by factoring out the I. Likewise, subtract this from both sides, and then factor out the J. And it's time to move over here again. Finally, divide by 2 to solve for V. Wonder if that looks any better if I a little less glare on the blackboard that way. Should have been doing that all along. So if you're happy to have the answer in component form, that's the X and Y components. The question doesn't ask for this, but if it's the speed and direction you want, just to kind of remind you of something I've said before. You get the magnitude of a vector from the Pythagorean theorem, which in this case, that number is so small, it's going to be rounded off to 3 significant figures. The answer is going to be 7.88. And for the direction, it's the picture that came with the question is apparently slightly misleading. The direction is actually just slightly below the horizontal axis because you've got a negative y component. The arctangent of y over x. back over here to the handout. Important point. Mechanical energy, meaning kinetic plus potential, need not be conserved in collisions. In the one that I just did, number 6, where the 2 and 3 kilogram objects collide, if you take the initial information, the masses and the initial velocities, you'll find that there's a little under 94 joules of kinetic energy there. If you then take the final velocity of each and put them into 1/2 mv squared, add the 2 kinetic energies up to get the total kinetic energy of the system, you'll find that there's only about 80.5 joules. So a little bit more than 13 joules of energy is gone. This is where I should sternly warn you that a common mistake in this part of the course is I'll give somebody, I'll give the class a test question where there's some sort of collision going on, and there's always that certain element that insists on using conservation of 1/2 mv squared. And as in this one that I just did, 1/2 mv squared kinetic energy does not have to be conserved because there are other kinds of energy it can be converted into. What typically happens is you lose some of it into heat, okay? These 2 balls leaving the collision site it's only a fraction of a degree with numbers like this. You'd have an awful hard time actually measuring it, but they are slightly warmer than before they hit, I mean. With momentum, there are no other kinds of momentum for MV to change into. So momentum is conserved in any collision. Kinetic plus potential need not be. The example that I put here in the notes was, I said, imagine I was standing here on a nice hard steel plate, and I've got something in my hand that I decide to drop. Well, if it's a nice hard steel sphere, like the ones that we use in the lab for this section, the ball is going to bounce. Or if it's a very hard rubber ball, again, same sort of thing. What we used to call a super ball when I was a kid. It'll bounce back up to practically the height where you released it. Approximately, you might lose a fraction of an inch, but pretty much all of the potential energy you started with is still there when it tops out after the collision. Now imagine repeating the experiment, only this time I have a handful of Jell-O, and I drop that on the floor, and this is what the final picture looks like then, okay? The Jell-O just goes splat and does not return to anything like the height it was dropped from. So here, mechanical energy was at least approximately conserved, whereas here, it's gone. The difference is whether or not the object is permanently deformed by the collision, okay? If you have a low speed collision between 2 hard pieces of steel, when the ball hits the floor, really it acts an awful lot like a coil spring. It kind of squishes up a little bit, and then it bounces back to its original size, and in the process of returning to its equilibrium size, it pushes hard against the floor while it's doing that, and that propels it back up into the air. Whereas if it is permanently deformed during the collision, well, there's a lot of internal friction as one layer rubs across another as it's getting all squished around. Or, if it's a collision between two cars, while the metal is getting twisted and bent, again, a lot of internal friction, and a lot of the original kinetic energy gets converted into heat. So that's, well, one other thing I should say, approximately equals in this case, but there are such things as collisions that are truly perfectly elastic, okay? Terminology. An elastic collision, or to be precise, a perfectly elastic collision, is one where the mechanical energy is conserved. The steel ball in this picture went through an approximate, focus is all fuzzed up again, isn't it? Well, you had a chance to read this earlier, I guess, but this is approximately a perfectly elastic collision. As a better example, consider the air molecules in the room where you are sitting. At room temperature, air molecules have an average speed of around 1,000 miles an hour. Now that's just an average. There's a whole distribution of speeds. Some are slower, some are faster. But with an average speed of something like 1,000 miles an hour, it's kind of goes without saying that it doesn't take very much time at all to get from one side of the room to the other. Air molecules undergo many collisions every second. If those collisions were not perfectly elastic, if even a tiny fraction of the kinetic energy was lost every time they bounced off of something, in probably less than a second, you would find yourself sitting in a complete vacuum because the air molecules would be just laying around on the floor. Since you have survived, this shows you that in that case, you aren't talking about something that's approximately elastic. Those collisions really are perfectly elastic. When you collide a couple of steel balls together, like in this week's lab, well, there it's a little more approximate. You may lose a few percent of the energy. Sometimes when people do that experiment, it shows up outside the range of uncertainty, and sometimes it's close enough that, just a minute, I need to pause this. Anyhow, the terminology is that if energy is, if you can get away with using conservation of the mechanical energy, that's called a perfectly elastic collision. Many collisions are inelastic, the most extreme example being a perfectly inelastic collision, which is one where the two stick together. For example, I'm pretty sure there's a problem in the homework where two football players run into each other and they kind of, when they collide, wrap their arms around each other and grab each other. Or another example would be like if you fired a bullet into a block of wood that was big enough that the bullet does not come out the other side. Whenever you see anything like that, that is as far from conservation of kinetic energy as you can get. So, point is, momentum is always conserved in any collision, but unless you're specifically told you can use energy by, for example, this example that's coming up next, number 7, says the collision is perfectly elastic. Unless it says There it is right there. Unless it says something like that, you may come to grief by trying to use conservation of energy. I've only got this one example left, but I need to do something else for a little while. So I'm afraid section 3 is going to be divided into 3 recordings, the last of which will not be terribly long, but I better stop here.